show you, or point out a couple things you could do with it, arguments you can make beyond what we did. But anyway, remember the rational root theorem said that if R equals U over B is a rational root to the polynomial, then what was supposed to be true is that, what was it, the numerator divides the constant coefficient and the denominator divides the top coefficient. Okay, and there are some assumptions here. This is supposed to be reduced fraction. And the other assumption is supposed to be all these AIs are integers. Okay, all the coefficients. Right, so this is, we proved this last time. And anyway, the one thing we did with it was just to show how you could find rational roots of a polynomial, because what it does for you, these last two, or these conclusions are very restrictive because they narrow U and V down to a finite set of possibilities. And then in principle, then you have a finite number of possible rational roots that could be roots. I mean, a finite number of rational numbers that could be roots. You could just test them and see if any of them are roots. And then, in theory, then you could just find rational roots of any such polynomial. Okay. So we did that a little bit in one example. We showed how to find one. Other applications I just want to show you. This kind of supersedes what we did with our previous irrationality proofs related to radicals, like square roots and nth roots and stuff and so on. But just to show you a different perspective, say on the square root of 2 discussion, you could show that the square root of 2 is irrational by using the rational root theorem. So like a second proof that the square root of 2 is irrational. And so the way you can argue that way is you could say, look, the square root of 2 is a root of the polynomial, which is x squared minus 2. That's kind of what makes it the square root of 2, right? If you square it, you get 2, so 2 minus 2 is 0. So it's, would be a root of this thing. So if you wanted to argue why must the square root of 2 be irrational, you can use the rational root theorem and say, if it somehow were the case that the square root of 2 was rational, then the rational root theorem would tell you that U is a divisor of the constant term, which is -2. Okay, and interestingly, V is a divisor of the top coefficient, which is actually 1. Okay, so what this tells you then that U would have to be plus or minus 1 or plus or minus 2. Those are the only divisors of -2. But V would have to be plus or minus 1. So what this means then is the square root of 2. The only possibilities for the square root of 2 would be, one of those U's over one of those V's. And that just amounts to plus or minus 1 or plus or minus 2. It would actually have to be one of those 4 numbers. And it's clearly not one of those 4 numbers, right? That's supposed to be clearly a contradiction. Those are the only possibilities for a rational root, and none of them are roots, right? You could square all those numbers and you don't ever get 2. So that's just the second proof. So could have just done it that way. So this could do something we did before by using this rational root theorem. We can also argue about what we said about the kth root of n. So just the other example, we just want to generalize this to other roots, say the kth root of n. Well, we proved something that said this thing is going to be irrational most of the time, but there was an out. right? There was a scenario in which it could be rational, but that scenario was when n itself is a kth power of an integer, right? So anyway, if you wanted to argue about this thing, the point is that this thing is a root of x to the k power minus n. So you can make a similar kind of argument. And notably here, though, v would be a divisor of 1, as it was before. So what happens here is that if the kth root of n equals u over v is rational, then in fact what must be true is that it must be an integer. Since that v is going to have to be a divisor of 1. And so that's kind of what we proved before. So if it's rational, then in fact it's an integer, and what that's saying is that n itself is the kth power of some integer. So it's kind of the same result we proved earlier, but you can also argue it through rational root theorem. So that's kind of nice. So it takes care of some of the things we did previously, but also a lot more. Okay, and okay, is that okay? All right, so anyway, if you, to generalize this, these are very specific kinds of polynomials, but if you come across a number that you just happen to know comes like to you as the root of some polynomial, you can argue it's irrational in similar ways, potentially, using this theorem. Okay. There was one more thing I wanted to show you about this. Do you have questions on this? Just one more type of an application. So this is something that feels like a thing you could actually do. Very hands-on kind of thing. So suppose you had some kind of polynomial which maybe was a mess like this, like some big scary polynomial that does have integer coefficients. Okay, now say you were doing something with the roots of this, and you're a modern person using technology perhaps, and you can always find roots of polynomials like on a computer, approximately. There are algorithms to approximate them as well as you like. So, say you did that, you'd find 3 roots, and let's just say we know that the roots are approximately, because you use some kind of approximation algorithm to find them, so they look in decimal form something like this. But let's just say, maybe like 5 digits or something. So here's one of them, here's another one, and here's a third one. Okay, and so you just did that much approximation work to find that the roots look something like that. Okay, now if you just have a finite chunk of a decimal approximation of a number, you actually, in fact, cannot tell if it's rational or irrational. Right? So actually something we do know about being rational is that eventually the decimal approximation would have to repeat. But you can't tell that from what you see here. And the eventually part might mean it happens like 20 digits down the line. Right? You don't see it until then. Okay, so anyway, what first comment is that if you just saw these 3 numbers and didn't know where they came from, you cannot tell if they're rational or irrational. Okay, but given we know where they came from, there is actually a way to answer the following question. Okay, without doing what we did before, where we just do an exhaustive search for rational roots. So here's what you can do. So here's just a nice little trick, right? So if any of them are, right? So if any of them are, or any of them is, and that would mean it looks like a u over v, right? And what that would mean by the rational root theorem is that v is a divisor of 78. Right? So if any of them is rational, like of this form, then the denominator the v, is going to be a divisor of the number 78. Okay, and so what that would mean then follows is that if you took the number and multiplied it by 78, the denominator would cancel into the 78, right? And you'd be left with an integer, right? So if you multiplied such a number by 78, you would get an integer. Okay, so the point then is that, like, if we multiplied by 78, we get an integer, necessarily. Okay, so the thing you can do in this little fun application is you can actually just take these approximate roots you found and multiply them all by 78 and just see if you ever get an integer. Okay, so you can take these numbers, just multiply by 78, right, and then see what happens. And I mean, that's something you would just get a calculator out and do it. And let me just show you what happens if you did it. So I mean, for the first one, you get this. Well, it's definitely not an integer, right? Way off, not close to being an integer. That's what you get for the first one. For the second one, if you multiply that number by 78 on your calculator or wherever, you get something that looks like that. Okay, and that certainly appears to be an integer. Okay, so that's notable. But the third one is not so much. You get something which, because of that 0.7, is quite far away from being an integer. Okay, so what seems to be the case here then is that, well, we got an integer in the middle. It certainly looks like an integer. Okay, so the second root over here, it looks like when you multiply it by 78, you get the number 27. So that in fact tells you that this root is 27 over 78. Okay, so you've actually sort of figured out what this thing is as a rational number. So this shows the second root well, I mean, it's extremely compelling evidence, I should say, that the second root seems to be 27 over 78, which, by the way, is, you can reduce this, divide by 3, and you get that. Okay, so, I mean, maybe that somehow wasn't true and it was off by some decimal digit way down the line, but it's extremely compelling evidence, and then you can check it. Like, once we now believe that's what the root is, you can plug 9 over 26 into the polynomial and just see if it works out. So it does, again.
The first and third one add up to an integer. Does that mean anything?
Well, yeah, that should be happening here. Let me say why in a second. Right, because they're roots of a quadratic with integer coefficients is what's going to happen, and so once you know this is a root, you can actually factor out like a 9x minus 26, something like that. So what can happen is out of this thing you could factor out a factor which will look like 9x minus 26, and you'll get a quadratic polynomial with integer coefficients, which is the other two are roots of. And what happens is I guess it's the middle coefficient of a quadratic is actually the sum of the roots, or maybe it's negative the sum of the roots or something like that. There's a general thing, like if you, but it has to do with the fact that they're both roots of a quadratic that has nice integer coefficients. And so if you ever have something like a quadratic which has, say, a modic quadratic, so it has a x squared coefficient of 1, when it's factored like this, where R1 and R2 are the roots, this looks like x squared minus R1 plus R2 times x plus R1 times R2. So what's also true but not clear is that it should be the case that the product of those is an integer too. Because the product would be whatever that constant coefficient is, and the sum is the negative of this coefficient. And those should work out to be integers in this case. Yeah. So that's good. It's a nice observation, and there's a good reason. Wait, is that true? Wait. Now I'm confused. Those don't add up to be integers, do they?
Well, 20.2918 and then 49.7082.
Oh, yeah. Okay, so after they got multiplied.
Okay.
Oh, yeah. Okay, so I think I lied in that instance. And then I claimed something I think wasn't true, which was that when you factor out this factor corresponding to the root, that the quadratic you get is actually an integer. I think it should be it should have rational coefficients, and you probably have to multiply them by 78 or something to get the integer. So it's okay. There's still value in what I said. It's just the argument was a little. You have to actually walk through it to see what the correct quadratic to take a look at is. And okay. Okay. So anyway, there is a reason. Okay. Sorry for that, but dig deeper and you can explain it this way for sure. Do you guys have any questions about this? Idea. So yeah, these other ones turn out to be irrational. Okay. All right, so we're going to move on to something else. Maybe closing questions on rationality or irrationality. Okay. So we are going to do. Well, it's kind of an interesting topic, I think. It's supposed to be maybe a little amusing, too. It's a familiar sort of thing. We're going to talk about Pythagorean triples. Which you all should know, I think, at least one of these things. So what these are integer solutions to the equation that is the Pythagorean theorem. Okay, so a Pythagorean triple this is a triple of integers, so it's 3 integers, a, b, and c. Which have the property that they satisfy the equation of the Pythagorean theorem, which is a squared plus b squared is equal to c squared. Okay, and so, I mean, this Pythagorean theorem, as we know, comes from a very geometric place. It's about right triangles. And the 3 side lengths of a right triangle, right, have to satisfy this. So what we're considering, are scenarios in which we have a right triangle in which the side lengths are all integers. Right? So a lot of times if you just prescribe values for 2 of these things and say what's the third, it often comes out to not be an integer, even if you start with integers. So it's kind of interesting when all 3 are integers. So this is what we might call or what people could call certainly it's another example of a Diophantine equation. It's a nonlinear Diophantine equation. That's how you think about it. I mean, all it's really meant when someone says we have a Diophantine equation is we're just thinking about trying to solve it, but only consider the integer solutions. So we'll take a real good look at this one. We won't be doing a general study of nonlinear Diophantine equations, to be honest, but we'll talk a lot about this one. And anyway, there's a very famous example of one of these. What's the really famous one? It's the easiest one. 3, 4, 5, right? So 3, 4, 5. Yeah. So I guess maybe I should have said, by the way, let me say positive. So we'll leave out things like 0, 1, 1 or something. Right? But anyway, 3, 4, 5, yeah, that's kind of the most famous. All right, so we'll just write this down. 3, 4, 5, right? We all know 3 squared plus 4 squared is 5 squared, or if you didn't know, you could check it anyway. Right? So 9 and 16 is 25. You guys know any other ones? 5, 12, 13. That's the second most famous one. 5, 12, 13. Indeed, you could confirm this if you need to. 25 plus, that's 144, is 169. Yes, how many more do you know? You know one? Yeah.
There is 8, 15, 17.
8, 15, 17, that's another one, yeah. Yeah, the equation's true. But anyway, there's another one I'll point out to you, which is this. This is a Pythagorean triple as well, but you might say, well, that's not terribly interesting. And the reason why that one's not terribly interesting is that it's just 2 times the numbers from the first one we had, right? So anyway, that, of course, just kind of points out that you can create things like this, right? So if you have some Pythagorean triple, you could just multiply all the integers in it by the same number, and then out pops a new Pythagorean triple, but there's something kind of uninteresting about it. Okay, they exist, but not so interesting. Okay, so this works, but the point is, it is a multiple of our friend 3, 4, 5. Okay, so 2 observations. The one I just said is that if you start out with a Pythagorean triple, you can make a new one by multiplying it by an integer. Okay, so 2 notes. First one, if ABC is a Pythagorean triple, then so is, let's say, k times A, k times B, k times C, where k is an integer. Let's just say a positive integer. So that's fine. The reverse way to think is maybe if I had something like this, I could perhaps divide by a common factor to produce something like that. So anyway, if you have a Pythagorean triple ABC, so if you had something like this where there was a common factor, let's call it D. So what we really maybe want to consider is something like the GCD of the 3 things. We never really spent much time talking about GCDs of 3 things, but it's the same concept. Okay, it's the greatest number that divides all 3 of A, B, and C. But anyway, if you had such a thing and D was the GCD, then for sure you could take A over D, B over D, C over D. Those would be 3 integers, and you could check for sure that the equation is satisfied, that they would be a Pythagorean triple. Okay, so anyway, that would be kind of notable because the Pythagorean triple that this construction would produce would be something in which they no longer have any factors in common, which seems to be the interesting thing to talk about, right? Like these ones are not interesting because they have a factor in common. And then if you had something with a factor in common, you could produce one where they don't have something in common. So we'll give those names. They're going to be called primitive Pythagorean triples. And that's what we're going to start asking questions about soon. So, definition, the primitive Pythagorean triple. This is one, meaning a Pythagorean triple, for which the GCD of all 3 is 1. Just note what that means, by the way. You can have this GCD be 1 in scenarios in which perhaps A and B are not relatively prime, or B and C are not relatively prime. But this is about all 3 sharing a common factor. It doesn't rule out the possibility that 2 of them share a common factor. Okay, so anyway, these 3 are primitive right here, as you can probably see after thinking about them for a moment. That one certainly is not. So anyway, we're interested then in talking about primitive ones, because all the other ones come from primitive ones. And now we can start asking questions like, are there infinitely many of these things? Okay, so questions we pose. Are there infinitely many primitive Pythagorean triples and if so, can we figure out what they all are? So is there, let's say if so, is there a way to generate them all? Or describe them all, and so, the answers are going to be, in both cases, yes. So that answer's going to be yes and yes. And that's where we're headed right now. So we'll try to understand the story behind all primitive Pythagorean triples. And so you can answer the first question without answering the second question. So there are certain families of these that are kind of easy to describe that don't cover all the possibilities. And so I'm just going to show you, just because it's mildly amusing. But let me show you one or two ways to generate these things. These are like little tricks that you do at parties or something. You want to impress all your friends. So here's one way. It's like a magic trick. Not really. But one way to generate Pythagorean triples. So what you could do is, this is just one recipe. It's not a comprehensive one in that it wouldn't answer the question, how do we get them all? It's just one way. But the idea is, start with any odd integer. So any odd integer, a, call it a. So what you do then is take a and square it. And so square a to make a squared. And then what you're going to do is take the square and write it as the sum of two consecutive integers. So we'll call those things b and c. So take a squared. There's only going to be one way to do this, but figure out what are the two consecutive integers with the property that they add up to be this odd number a squared. And then the statement is that the a, the b, and the c you've made are in fact a primitive Pythagorean triple. Okay, so then a comma b comma c is a primitive Pythagorean triple. That's the claim. Okay, but anyway, if you want to just see this in action. So this is, the claim is it works for any odd integer, let's say positive or something. But let's not take one. Okay, so anyway, the way it looks is like this. If you want to just see it in a hands-on way. So just a couple quick examples. First example to consider, if a is 3, right, then a squared is 9. And you say, how can I write 9 as a sum of consecutive integers? And the answer is 4 plus 5. It's the only way it's going to work. Right, and so 4 and 5 will be our b and our c. And so this gives us 3, 4, 5. Okay. But anyway, it's going to work for any odd starting point. You want to try 5, right? So if you start out with 5, recipe is square it to make 25, and then say, how do I write that as the sum of consecutive integers? Just two consecutive integers. The answer is 12 and 13. Right, and that's where your 5, 12, 13 comes from. So since it's maybe less well known, we can look at the next one. And so if you start out with 7, a squared is going to be 49, which, so you'd want to take like about half of that, right? Which is So anyway, the claim is it always works. The one part of this is actually kind of clear. So if you believe you get a Pythagorean triple, it's not supposed to be tricky to see why it's primitive, because it's got two consecutive integers, and how could they have any factors in common, right? So the GCD is going to end up being 1 because it has those consecutive integers. They'll have no factors in common. So anyway, if you wanted to know why does it work, you could really just prove it algebraically. You just have to check that this recipe will always lead to a solution of the equation a squared plus b squared equals c squared. And if you wanted to see why it works, I'll just show you why it works. So you just prove it algebraically. So let's just prove it works. So the idea is that a is supposed to be odd, so you can write a as, let's say, 2k plus 1, and that's the starting point. That's an arbitrary odd number. And then if you square it, what happens is you get 4k squared plus 4k plus 1. And then you say, how do I write that as the sum of two consecutive things? And then if you take a moment, you want essentially half of this. Actually, you want half and then round it down, round it up. You get your two numbers. But if you took half of this, you get 2k squared plus 2k plus a half, so you round it down to get this. But if you rounded it up, you'd have the plus 1. And those, in fact, are consecutive integers that add up to this thing. So this is your b and your c. Okay, so what you can do if you want to just justify why this works is you can verify that the triple, which is 2k plus 1, 2k squared plus 2k, and then 2k squared plus 2k plus 1, this being your ABC. You can just verify it actually satisfies a squared plus b squared equals c squared. And so what that would mean is, I'll leave it to you to do it, but like algebra, just like plug this a and this b into here, square them, add them up, do your algebra, combine things together, and show that what you get is the same as what you would get if you squared that thing right there. Okay, so just you verify. Once you have something that you think is a Pythagorean triple, you can just check it actually satisfies the equation by putting it in and being sure it's true. Okay, so anyway, that would always work. And that would actually answer one of our questions, by the way, which is, are there infinitely many primitive Pythagorean triples? Because you could do this for any odd a, so you can generate infinitely many primitive Pythagorean triples this way. You can make one for each odd a you'd like to make one for. Okay, so that's true, but anyway, the interesting part of the story is that this is not the complete thing. Okay, these are not all of them. All right, so there are more, and that's something we'd like to explore. We had one on the board, what was it, 8, 15, 17 or something? That does not fall into this form, right? Because these are ones where the b and the c are always just one integer apart. So these are not all of them. There's a second recipe. You can just look at it briefly if you really want to really impress your friends. It's a different little magic trick. So this one you start out with a multiple of 4. I'll just show it to you really briefly. Maybe we'll not dwell on it too extensively, because it's another fun little example of a family of these things, but it's still incomplete. There's more out there. So I'll just show you another construction. Which is, this one you start with a multiple of 4. So let's call it a equals 4k. It's a multiple of 4. Okay, and then what you do with your multiple of 4 is, like we did before, square it. what you get and divide it by 4. So if you square it, you get 16k squared and divide by 4. That would give you 4k squared. Okay, and then what you would do to this number, sort of similar to what we did before. You want to write it as a sum of two things, but now they'll be separated by 2. So we're going to write as a sum of 2 odd integers that differ by 2. So that is like, we want to write this 4k squared number basically as 2k squared minus 1 plus 2k squared plus 1. Right, that adds up to 4k squared. But anyway, that's supposed to be your B and your C. So the claim here is, well, those are your B and your C, but the A is just the one we started with. So the claim is that, this our original 4k, and then 2k squared minus 1, 2k squared plus 1. This is a primitive Pythagorean triple. Okay. But anyway, it's just another recipe that's amusing to do with actual numbers instead of thinking of the algebra. You could think of the algebra. You could plug it in, verify ABC satisfies a squared plus b squared equals c squared. These will give you different ones in general. They are going to be, as we'll see in a second, these are going to also be primitive. The key to understanding that is to notice that these differ by 2. So that doesn't leave open a lot of options for common divisors. Right? If two numbers differ by 2, then the only potential interesting common divisor they could have is the number 2. But they're actually odd, so they don't have 2 as a divisor. So anyway, it works out to be primitive. But if you wanted to see a couple of quick examples, you could take, say, the number 4, right? And then what we said was square it and divide by 4. So a squared is the next step, right? You take a squared is 16, and you divide by 4, and you're back at 4. And then what you're supposed to do is write this as, what did I do? I feel like I did something wrong. Was I supposed to divide by 2 and not 4? Yeah, I think I messed this up. I'm sorry. What, I'm sorry. Yeah, I'm supposed to divide. The way I explained it was totally wrong. So, let me just, it wasn't supposed to do this like right as a sum. What you're supposed to do is just basically this. I goofed, sorry. It would have been correct if we divided by 2, but let me just write it a different way. So square it, divide by 4, and then what we want to do basically is just take the 2 odds on either side of this thing. So. Okay. Yeah, if I said divide by 2 and kept what I said, it would have been fine, or we could modify it this way. I'm sorry, this is wrong. So then it's supposed to look like this. Anyway, the way this one's supposed to work out is once you divide by 4, what you're supposed to do is take the integers on either side of 4, right, which are 3 and 5. Okay, so what would happen here is you want to take b equals 3, c equals 5. Okay, so what this one actually gives you is 4, 3, 5, which is really 3, 4, 5, which is one we're already quite happy with. Okay, and then that one we've seen already. But then this will give you different things if you do this correctly. So if you take this one, let's just do one properly. If you take 8, you square it, you get 64. Okay, and then if you divide that by 4, 16. And then the point is you're supposed to take the integers on either side of 16, so 15 and 17. Okay, and that's where you can see 8, 15, 17 pop out. Okay, and then you can make more if you're really interested, right? So you can start with 12, start with 16, start with 20, anything like that. Okay, but anyway, this is still not complete, and these ones will always produce triple where these differ by 2. You have odds that differ by 2, and it's still incomplete. So we don't want to keep pursuing these little fun games, but like we're going to want to eventually just have a nice big classification theorem that gives us the entire story, of which these are just a little slice of. So I mean, I'll actually show you that. Like, we'll state the big theorem. It's a theorem we're going to prove. Well, certainly not today, but we'll start working on it next time. But I'll tell you the theorem now, and then we can apply it a little bit in whatever moments we have left. So here's the main theorem of the section, which is the classification of all primitive Pythagorean triples. So suppose ABC, let's let this be a primitive Pythagorean triple. Okay, so here's a couple things you can say. First of all, the C, so-called hypotenuse, will always be odd, first of all. So C is odd. Okay, now the other two, A and B, will necessarily be, it'll necessarily be the case that one is even and one is odd. Okay, so exactly one of A and B is even, meaning the other one's odd. Okay, and conventionally here, we'll say B is the even one. Let's say B is the even one. If it wasn't, let's relabel it so it is. Okay, and so here's then the explanation for where they come from. They're going to exist a pair of different integers, so relatively prime integers m and n. We'll say m is less than n. We'll have this pair of relatively prime integers. These now, one is even, one is odd. Such that the entire triple comes from them in the following way. So A is going to be n squared minus m squared. B is going to be 2mn. And then C is going to be n squared plus m squared. Okay, let me just add the remark further. If you build a triple this way, it will be primitive. So further, any triple constructed this way is going to be a primitive Pythagorean triple. Okay, so there's some kind of correspondence being set up here between primitive Pythagorean triples and the pair of n and m, right? Where it's not just an arbitrary pair of integers m and n. It's ones that have two conditions satisfied. They're relatively prime, and then they have opposite parity, meaning one's even, one's odd. Okay, so any primitive Pythagorean triple comes from such a pair of m and n, and then conversely, if you find any, if you take your own pair of m and n, as long as they satisfy these conditions, and you build this thing by these formulas, you will always get a primitive Pythagorean triple. So this is the main theorem. This will take a bit of effort to prove, so certainly we won't prove it right now, but we can actually look at it, so and just play around with it a little bit, just to do a couple quick examples, since we have a couple moments. So you can just start out with some examples. So the idea of the examples would be just building them, like say pick an m and an n that satisfy these conditions. So for example, if n is 3 and m is 2, you can see what does this give you, right? So one's even, one's odd, they're relatively prime, so it's all a go here. And then n squared minus m squared would be your a, that would be 9 minus 4, right? So your a is 5 in this example. The b would be the 2 times their product, which is 12. You see where this one's going. And then the c would be the sum of their squares, which is in fact 13. So this is where the 5, 12, 13 one comes from. Right? And you can do these as much as you want. We'll just look at a couple. Guess in the time we have. So what happens if you take 4 and 1? Right? So you just follow this through. So that's again 1 even, 1 odd. They're relatively prime, so you're allowed to take 1 here. It's not a violation of anything. And so here the difference of the squares would give you 15. That's A. Twice their product, that'll give you 8. And the sum of their squares, that'll give you 17. Okay, so here's our 8, 15, 17, 1. Okay. Okay, well, let's do one more. We'll get one we never solved before. I think, yeah, here's one we never solved before. Okay, so just, again, the point is, take any pair you want, 1 even, 1 odd, as long as they're relatively prime. And by the way, well, maybe next time we'll look at what happens if you violate one of those things that we're supposed to assume at that point in. But anyway, here's one that's a valid thing to work with. A would be the difference of their squares. A is 45. B is twice their product. So that's 14 times 2 is 28. And then C is the sum of their squares, which is 53. So here's one we haven't seen yet, which is 45, 28, and 53. Okay. So anyway, the claim is they all come from